We looked at eliminating data races by eliminating the first two conditions in the list. That leaves us with plan C, which is to eliminate mutability, our last condition. Now, the idea of eliminating mutability is something that's pretty common in functional programming languages. That's one of the key ideas in functional programming languages, is that you don't have mutable data. And for concurrent and parallel programming, that's great. As soon as you don't have mutable data, then you aren't going to have data races, because you can't mutate the data anyway. That does require some work to program in a functional style, although once you're comfortable programming in a functional style, it doesn't seem like that much work. But we're going to look at a concrete example of how we can get even more sort of benefit from moving to this sort of functional style and taking advantage of a system that is really built around working in a functional style with concurrency. So the language that we're looking at as an example is Elixir. Now, Elixir goes a little bit further than some of the other programming languages that we could talk about. For example, Haskell might be the sort of most straightforward example of a language that really does use plan C, and the plan is just we're going to eliminate mutability. We'll also be talking about Clojure in a second, which is a good example. Objective Camel would be a good example, but the language that I want to look at first is Elixir. We're going to look at Clojure, but it does things a little bit differently. Now, in Elixir, what we have is a language that is based on another language and the associated runtime. So Erlang is a language that was developed in the late 1980s at Ericsson, specifically for telephone switches. When I talk about telephone switches, I don't mean switches for cellular telephones. I mean switches for wireline telephones. And the number one design requirement that they had for wireline telephones was reliability. They didn't want to ever have to be in a situation where the phone system would go down. It's okay if occasionally the system drops a phone call, but it needs to be that if your phone call gets dropped and you hang the phone up and pick it back up again and try to talk on the phone, you get a dial tone and you can make another phone call. And in order to get that level of reliability, that means no downtime even for upgrades. And so in order to get actually no downtime, and they talk about no downtime in terms of like 99.999% uptime, they start to get into, is it 5 nines or 6 nines? And the way to do that is no longer just a question of software design, because hardware fails more frequently than that. So in order to get that level of reliability, you have to be able to live through hardware failure. And the only way to live through hardware failure is hardware redundancy. You need to have two separate pieces of hardware, two separate computers, if that's what you're dealing with. And things need to be set up in such a way that if one computer just completely breaks, if you like spill soda in it, then the other computer can notice and take over. And immediately, that means we have a distributed system. So our goal is reliability. Reliability means hardware redundancy. And hardware redundancy means a distributed system. And a distributed system means not just that we have concurrency and we have parallelism, but we have sort of the most extreme case of those things. We have to be able to communicate between one machine and another machine. We can't have reliable things like a shared clock that are just things that we assume all the time. Instead, we have to be able to build into the system support for just having separate code running in two places and having them synchronize and all that fun stuff. So the result was a virtual machine called Erlang, built for this telephone switch reliability thing. And that worked nicely through the 90s. And then we had this interesting thing happen in the early aughts where desktop computers and servers and even cell phones all ended up being multi-core machines. And suddenly this built-in support for concurrency as the result of these design goals that were built into Erlang historically meant that all the things that Erlang already did well were things that we needed to solve in modern computers. Now, Erlang had one thing that it didn't do all that well, and that was language syntax. Erlang syntax is not great, and when I say not great, I mean it's sort of horrifying. It is a syntax rule in the Erlang programming language, not like a semantics rule, not some like deeper thing, but a syntax rule that in an if expression, so if you say if and then you put a condition in, you can't call user-defined functions in that condition. And there's reasons for that. It to some extent makes sense, but it's also horrifying. That's not the only thing wrong with the Erlang syntax, but it's indicative of the sort of thing that you have to deal with in Erlang. And so Elixir was a new programming language that was developed specifically to take all the benefits of the Erlang virtual machine, the Erlang runtime, the Erlang standard library, Erlang support for concurrency and distribution, and just put a slightly better syntax on it. And Elixir is nice enough that it's now the language that's like starting to become popular for web development, whereas Erlang, less so. Erlang does see some real use. Facebook Messenger used to use it, WhatsApp uses it. It's frequently used in this sort of messaging environment that is obviously pretty similar to the telephony environment that it was built for. But Elixir also sees sort of broad adoption in some other areas. For example, the MBTA uses it for their API. So this is the language that we're going to be taking a look at, Elixir. Now, the key trick that allows Erlang and Elixir to do their thing, this reliability and concurrency thing, is they have this concept of processes. Logically, these are a lot like operating system processes. They are separate flows of execution that don't have shared memory. That gets back up to condition 2 here, plan B, not having shared data. Elixir and Erlang appear to do that. But that means that in order to communicate between processes, you can't do it by mutating shared data. And it's really the mutation rather than the shared data. But either way, we can't do that. So instead, Erlang has built-in message passing. So that's our key trick for inter-process communication, is passing messages. And that's a built-in feature in the virtual machine and the standard library. So let's go ahead and see how some of that works for parallel and concurrent programs. Let's go ahead and open up a Elixir file. So Elixir files have a .ex file extension. And in Elixir, code mostly has to be in a module, so we'll start off by defining a module called demo. Now, the way we define functions in Elixir is with def, and we're going to start off with the most boring example, which is a Fibonacci function. So we're going to say that Fibonacci of x is something, but we're going to use a neat trick. We actually can have multiple clauses for each function. So we're going to say that fib of x when x is less than 2 is x, and fib of x otherwise, so this is our second clause, is going to be fib of x minus 1 plus fib of x minus 2. So this looks like two functions. It's one function with two clauses, and these get compiled in such a way that the runtime will first try the top one. If this guard condition here doesn't match, it'll go on and try the second one. So this lets us pretty easily define this recursive function with a little bit less indentation than in languages that don't have this particular feature. So we'll compile this with Elixir C, and then run the interactive Elixir shell IEX. Then we can say demo.fib. So we're running the function in the demo module named fib, and we'll say demo.fib of 1 is 1, demo.fib of 5 is 5, demo.fib of 10 is 55. Those look like right answers. So there is a simple sequential program in Elixir. So the next thing that I want to do is, this fib thing is a sort of slow function. We saw that in the JavaScript example. So I want to try to use parallelism to speed up a slow computation. Now the slow computation that we want to do is going to be to call fib several times on several elements in an array. So we're going to write a function called Mapfib. And what it's going to do is it's going to call enum.map. So that is the standard functional programming sort of loop function that loops through an array. And we're going to give it as input an array of 38s. So we're going to give it an array of 4 38s. And the function that we're going to call is going to be fib. And this is sort of funny syntax. Again, Erlang has funny syntax, and Elixir inherited some of that because it has semantic meaning. But this line, this expression here, is just talking about the fib function with one argument in the demo module. So if we compile that, if I can remember how to compile things, I can do it with the C built in the IEX shell. We can then go ahead and see that this Mapfib function is kind of slow, but it's taking long enough that we can immediately see how slow it was. We'd like to have timings. So I'm going to go ahead and use the built-in timer in actually Erlang. And run exactly the same thing, except using this timer. And yeah, the syntax for this gets a little bit more complicated, but we're just saying we're passing timer 3 arguments, the map function that we want it to, or sorry, 2 arguments, the map function that we want it to run, then a list of arguments that it's going to pass the map function, one of which is another function. So it's going to go ahead and run this, and then we're going to print out how long it took in seconds, and then we're going to return the value. So now when we run that, we find out that it still is going to take a little while, but this time we're going to get a time on it. It turns out that on my computer, that thing takes 4.7 seconds. But we can see immediately that the 4 numbers here are each being computed separately. That means we can run them in parallel, and if we run the 4 calls to Fibonacci in parallel, we should be able to get a parallel speed up. So we have these processes that the Erlang virtual machine provides us. We can use those to build a parallel map function. So this is going to be just like the built-in enum.map function, except it's going to run each instance of fib in a separate process. We want to pass in our list and our operation, and then what we're going to do is we're going to call enum.map over x's. We're going to pass it a function. This is how we do an anonymous function. So a function of x, we're going to run it as an asynchronous task. That's just a process in the Erlang virtual machine. That's going to take another anonymous function, where we're going to call our operator on our value x from the array. And so now we have an array of process IDs one for each one of these tasks, and they're all running in parallel because they start running as soon as we create the task. And what we want to do is take that result, and now we're going to map over that result again. And when we pipe, that's going to take the return value of this and jam it in as the first argument here. And what we're going to do is we're then going to await on each one of those tasks. So we'll spawn 4 tasks, let them run, and then wait for all 4 tasks to finish. We can go ahead and take our Mapfib function and copy it, make it be a pMapfib function, and then instead of calling enum_map, we're just going to call pmap, which again has 2 arguments. We're going to run it on the same set of 438s. We're going to run it with demofib with 1 argument as our thing, and we'll see how long that takes. So we have to recompile the module, and then we'll call demo pMapfib. And it turns out that running it in parallel with 4 Erlang processes, which Erlang can schedule in 4 separate operating system threads, which on this machine should be able to schedule into 4 separate CPU cores, runs in 1.4 seconds instead of 4.7, which gives us a speed up of about 3 1/3, which isn't bad for going to 4 processes with not that much work. So there is how we can easily do parallelism in Elixir. And we do that without any special fear of data races, because there was no shared data and no mutable data. With neither, we don't have to worry about it. Let's do an example of just regular concurrency, just to show the sort of neat stuff that we can do here. So still in the same demo module, I'm going to add a couple more functions. Def printer. So what this printer function is going to do is we're going to run this printer function in a separate process, and it's going to sit and wait for messages. When it receives a message, it's going to try to match that message against patterns. First one is going to be a tuple of say and then message, and if we get that particular pattern, it's just going to print out the message. Any other message, so this is just a pattern that is just an assignable variable, it'll match anything. So if we get anything else, we're going to say IO puts and then we're going to print out that that thing that we got sent. To start that, we're going to call the start printer function. Oh, and we don't just want to do this once, we want to do this forever. One of the neat things about the Erlang virtual machine is that it requires tail call optimization as part of the specification, so we can safely have a function that calls itself recursively, and this gives us an infinite loop with no additional stack space. Tail call optimization says that if we have a function where the return value from that function is another call to the function with no additional work after that, the compiler can set things up so that it reuses the stack frame. That's a common optimization, and some of these functional languages make it mandatory so that programmers can rely on it for infinite loops, because we don't actually have traditional style loops in this language. There's no while loops or for loops. If we want to do loopy sort of stuff, we must use recursion. All right, so we're going to start printer. So to do that, we can use this task module again, start task, and we'll just pass in printer with no arguments as our thing. So that's exciting. We have this task that we can start that will print things when it gets messages, but we'd also like to have another process that will send it messages. So we'll create a function called sender, which will be a sender process. It is going to do send. Oh, it needs to take a process ID and a number. So it's going to send to our process ID, it's going to send the message, say, and then that number. Then we're going to sleep for 1,000 milliseconds. Then we're going to tail recurse and loop. So this is going to run forever, but it's recursive with a delay. So it's just going to sit there and run forever, but it's not going to like take up infinite CPU time. And unlike with JavaScript, this Erlang virtual machine really is able to execute stuff in parallel, handle full concurrency, handle multiple CPU cores. And so this is just going to take up a trivial amount of CPU time once every second to do that small amount of work. So then we can start that process. We'll make a start sender function. And that's going to start our sender with, let's do it this way, demo, sender, and then we'll pass in our 2 arguments, which is our PID, and we'll start it off at an integer of 0. There's a bunch of ways to express this sort of like start a function thing. We've seen at least 4 syntaxes here for functions. It makes sense if you spent some time with Elixir. It looks sort of funny if you haven't, but that's true in every programming language. So I think that's the code that I wanted. Let's see if it compiles. It compiles, so we're going to say something is going to be start printer in our demo module. Okay, so we got back OK PID, so I'll say OK PID is X to unpack that PID. Now I've PID in the PID variable. We can say send to that PID foo, and it's going to print back foo, which makes sense. This was not the say case. If we send it say hello, it'll go ahead and print out hello. It turns out the return value of send is just the thing that we sent. That's interesting. But the thing that we're actually trying to do is say start sender, pass in that PID, and then, yeah, that's all we need to do. So we start a sender, and now we just start printing numbers every second, because we have 3 processes running now. We have the shell process that printed the IEX prompt for us. We have a printer process that prints out numbers when it gets messages. And we have the sender process that's going to send a message to the printer process every second. We can see this very clearly if we start another sender process. Now we have 2 sender processes, both sending numbers to the printer process, and we have the printer process which prints numbers when we get them. So this is concurrency in action, and it is a way to handle concurrency that's like pretty effective. There's one more part to this story. I said that Elixir is a good example of plan C here, where we're restricting mutability, and isn't necessarily a good example of plan B, where we restrict shared data. Although we are restricting shared data because processes logically don't share data, it turns out that if we allocate some large piece of data, say we read an entire like frame of a video from a file, if we really didn't share data, and we took that data and passed it in a message from one process to another, that would require copying it. Each process in the Erlang virtual machine has its own separate heap. And so if we pass a message from one process to another process, and we really don't do any sharing, it requires copying from one heap to another heap. But Erlang has an optimization that for large data, and when we're not passing messages between machines, remember Erlang's designed first for distributed systems. And if we're passing messages between machines, there's no way to share memory anyway. You have to send the data across the network. Naturally, you're making a copy. But if the 2 processes are on the same machine, and we're sending a relatively large piece of data, more than a few bytes, the trick is the data is immutable. So whether we share the data or not isn't something that the user can ever tell. We can't mutate it, so there's no way to tell if it's shared. And so we have a separate heap for large objects. That heap is reference counted, and if we pass something that's more than a few bytes, a few hundred bytes, from one process to another process, it's not getting copied. We're copying a shared reference because we can, because it's immutable. So there is One of my favorite languages, Elixir. Turns out that we have some more plans, so I'll be back to talk about those.